hope you all recovered as I did from an amazing meal last night. Really fantastic. And I would thank the ESRF people for going above and beyond the call of duty. So our first speaker this morning is Smirnov, who will talk about applications in finance. Okay, Ivan.
Hello, everyone. My name is Ivan, and I think I'm the only guy from finance here, sort of a black cat, with all the beamlines and atoms and molecules and stuff, which is pretty cool. Can you hear me well? No?
Is it working?
So, yeah.
Maybe put it a little bit closer.
Okay. Is it better?
Yes. Yes.
Okay. So my name is Ivan, and I work in a American trading company in Dublin, Ireland. So I'm a quantitative researcher. Myself have a PhD in statistics, and my particular role is in ultra high frequency trading. So we build algorithms, we build software, and we build specialized hardware to trade on financial markets with like sub-microsecond speed, which is a pretty challenging task. And naturally, we have to deal with humongous amounts of data, which is humongous to us, but maybe not by scientists or physics standards. So it's still not terabytes a day, but it's still quite a lot. And so today I'd like to talk about, well, two things. So first about the financial data and how it looks like, maybe how it's different from the data that's typically captured in physics experiments, how we use HDF5, and a few issues and stumbling blocks that we've observed. Okay, so let's start with financial data. So unlike the scientific experiments where you would typically run an experiment and you would record a bunch of data yourself, you would structure it any way you want. Maybe you would use some standards like Nexus and share it with other scientists. In our case, most of the data comes from external sources. And the majority of this data comes from the market data comes from exchanges where we have to record it. So you would literally plug in a cable into a wall socket that you pay for, and you capture a bunch of UDP packets, and whatever you do with it, it's up to you, right? So it's a bunch of binary data that's not tabular. Second type is reference data, which is so once a day each exchange would publish like a huge half a gigabyte XML saying security number 1234 is Apple stock, and this is this and that. So explaining it's sort of like a mapping of numbers to real things. And then the second type of data is internal generated. So it's the data that we generate ourselves. It's computation results, so we can run some machine learning models, and which would yield tons of outputs and maybe some tests. We need somewhere to store them. Computational pipeline caches. So if we have thousands of tasks running on a cluster, each task consists of maybe 20 steps, and if we've already run 10 of those steps for similar inputs, we can detect that and skip them instantly. But those caches need to reside somewhere, and that's another use case for HDF5. And then pre-processed data, it's if you have to do the same thing over and over and over, maybe reshape some market data, like filter it or slice it, where we just pre-process it and store it somewhere permanently. So let's talk a bit about market data. So that's the most important type of data for us. And most downstream tasks use market data. Like the typical use is you develop some kind of strategy, maybe you have some idea, would this work, would this not work, maybe you want to test that something works correctly in production. So you would want to replay the market as if you were the exchange, like step by step, bit by bit, and so you would build the books for a particular instrument, and for this you need native market data. So native market data is what you capture from the exchange, those like raw UDP packets. Okay, and then so you can then pretend to be that exchange, and then you can literally apply it one by one. And it typically looks like it typically looks like this. Someone added an order number 12345 with this price, etc., and sometime later you would get a message that the order number 12345 has been deleted, or maybe there's been a trade that matched some order ID. So you need to maintain a lot of state, and it's very exchange specific, right? So each exchange has its own protocol for this binary data. It's not tabular, it's typically message based. So the messages can be spread over multiple packets, multiple UDP packets. They can contain multiple nested messages that contain multiple nested sub-messages, etc. So each exchange publishes its own protocol specification, and it can get pretty big. So it can be like 10,000 lines of some XML or JSON, right? And what's worse, they update those protocols like every year or maybe a few times a year. So they try to be backwards compatible, but they're like, okay, we've added a few new fields, we've added a few new fields. So you need to not only have a proper like parser decoder, you also need to know which one to apply to like a specific stream. In order to build the book and in order to replay this market state, you need an exchange specific engine, so to speak, like market engine, right? So that's native market data. Then there's market data from external providers. You may have heard of Bloomberg, for example, and it's one of the most popular providers. So they pre-aggregate this data, and let's say like every second they would publish you a price and volume for a specific instrument. So the traders can just look on screen and see things like tick. And we capture that as well. Then there's reference data, there's huge files published once a day. So typically these are captured daily by the machines we have installed on the exchanges, and they're stored daily in this like raw packets capture format, which yields a humongous number of files across hundreds of exchanges. And so as I've already said, most downstream tasks and jobs have to use market data to do anything really. So native market data, as I've already said, it's raw packets captured. So each exchange has its own protocol or protocols that change for different days, different streams. It's the worst kind of data to work with if all you want is like some pandas data frame, because it's message based, it's nested, it's not tabular. It may be deeply nested, but it can be tabularized with a bit of work. And by a bit of work, I mean a lot of work. Really, I'm not gonna delve into details here. It may also be considered proprietary, I guess, because it really is quite a lot of work. But you can, and by doing that, you can end up with a bunch of structured, like one-dimensional structured data sets, basically, where your fields are some of those fields in those like messages and sub-messages, and the main axis is time, really. Okay, and you can use those to replay the market. There's two ways to do this. The classic way to do this, and that's how we've been doing this for a while, is the direct approach to replaying the market data. So you can capture those packet streams, and maybe you can like zip them or something. And then if you want to replay market data on a particular day, you can decode this packet stream. So you need to know that I need this particular parser for this exchange, for this product. Okay, then you can feed those packets to an exchange-specific engine or like a book builder, which will yield some like exchange-agnostic, maybe prices, volumes, orders. And you can then build some computations based on that. It's very, very slow because you have to go all the way from those from the packet level. You have to parse everything every time. If you're doing this in C++, then you have to link your applications to various exchange-specific decoders and parsers. And if your application needs to deal with multiple exchanges, it gets big really quick. So an alternative way is you can decode those packet streams and convert it to format agnostic HDF5. So it would look the same, but maybe it will have different data sets, the different names, but they would have the same meaning at the very least, right? So you get rid of the of those binary blobs. You've decoded that. So you can go one step further and actually run that market engine and emit exchange agnostic data and store that in HDF5. And then the downstream applications don't have to worry about all of the stuff at all, about all the low-level details. Okay. So how does HDF5 fit into all this? So first, as I've said, you can generate format agnostic, exchange agnostic data, which is very nice. You can store that permanently. There is a natural hierarchy of exchanges, products, dates, instruments, and products that plays pretty well with the hierarchical nature of HDF5. Attributes are pretty nice to store metadata. So once you go through all those conversions, you can retain some metadata on where these files came from, what was the IP address and port that we captured on, and stuff like that. Now there's two things. The write speed doesn't matter to us at all. We don't care if it's 1 second or 2 hours, because it's, as long as it's done by when the morning starts, really. It's done by nightly jobs, so they that start running at midnight. So as long as they don't take more than like 8 hours, we don't care. But the read speed does matter a lot. So like the last thing you want to deal with is a bunch of like angry mathematicians. So whether it's 100 milliseconds, 200 milliseconds, we do care about that like a lot. Now this data is extremely compressible with shuffling. So you can get something like 10x compression ratios, like 15x, mostly because the data is very similar, as in, so you have a price of like 101, 101, 101, and 101.1, etc. So once you shuffle that like bitwise or bytewise, you basically get a stream of ones, like million ones, and then million zeros, things like this. So typically you end up with something like maybe 0.1 or to 10 gigabytes per day per stream. There's multiple streams in exchanges. There's many days a year. So you end up with tons of files, and this is compressed HDF5. Now, just a few words about internal data. We use Agedefy to store and share both source data and results, computation results. We use Agedefy based caches for computation pipelines, as I've already mentioned. We use that to store structured application logs, both by application, both production applications that run daily, and then we convert those logs to HDF5, so we can then track, did things go right, did they not. This could also be machine learning applications where like a job runs for 5 hours and emits a bunch of like data frames and things like this. So it makes it a lot easier to trace what actually happened, and like in Egypt notebook, for example. And finally, most importantly, it's just a single data format to rule them all. So whether it's like C# on Windows, it's Linux, Python, C++, we always have a data format to communicate between teams, which is extremely important. So we don't have to spend time arguing on that, and it's schemaless, so we don't have to maintain schema versions and things like this, like we've brought above. So as I already mentioned, it's a Agedefy. It's cross-platform, cross-language, it's self-contained, and schemaless, which is very important. It's great Python support, by which I mean H5. It's awesome compression, which is C-BLOSC. Low entry barrier, which is pretty important for us as well. If we have like an intern, for example, and they've never seen HDF5, that they have no idea what it means, it would take us 5 minutes to just get them started, and they don't really have to understand what's going on. They just like H5 file, read whatever. They have the data, they can go on. Reasonably fast reads. Reasonably, unless you're starting to read things in columns in multiple processes and things like this. But typically, if you read the entire data set, it's very fast, even on NFS. So that's mostly it for the first part. The second part, actually, initially this wasn't planned to be a talk. I've contacted Elena and mentioned that I had a few questions and we have a few things that don't really work. And she was like, well, you should do a talk about this. So, so like a few stumbling blocks, maybe a few suggestions or a few ideas that we can discuss. I've asked my colleagues to send me an email with things that annoy them the most. So here are a few things that you may not be aware of. So first one, if you try to create a data set with several thousand fields, I'm not sure if anyone does that, but we do sometimes, then you can't do that because there's a 64K limit on the object header size. I tried to track this number in the SVN history. I found a commit 17 years ago, and that commit just renamed that 65536 to some header max size or something. So this kind of reminds me of the Bill Gates quote when he said that 640K ought to be enough for everyone. It's just like editor. Again, I'm not sure if I'm not sure how changeable is that or how adjustable is that. Would that break things or not? I haven't delved into the internals, but yeah. So that's one thing. Another thing is for the C++ API. If you deal with tons of structure types, which we do, one of the things that is not so nice, if you have like hundreds of those types and maybe thousands of fields, if you want to serialize all that stuff, you have to generate those comp type, compound type data types manually every time. And if you have an application that depends on your application that has to do the same thing, now that application has to do the same thing again and again. So all the downstream applications have to reproduce that stuff manually at runtime. And it gets much worse with nested structs and classes because you have to do it just explodes pretty much. Then you have to map all the special types like enums, etc. So you end up with tons of boilerplate like all over the place. And we were trying to find some hacks to allow us to avoid that. And one of the things that seem to work is something like this. So you have an enum and struct, and you just no, this is the idea is borrowed from PyBinds. If anyone has heard about this library, like PyBinds 11. So at some point a few years ago, I've added a support for structured arrays in NumPy, and this is pretty much mostly copy and paste of that, which seems to work. So basically, you say here you're saying, hey, I have an enum, it has these fields. I have a compound type, it has these fields, and this is a header, and all the downstream applications that import this header, they now have magical access to this data type, to the compound type. You don't have to do this ever again. What it does, so now we can do stuff like this. So this is some downstream application that includes that header, and you have a vector of those shape structs, and you can just say, okay, write array of that stuff. You don't have to deal with those comp type things ever again because it's already been defined automatically for you. And how it works, basically there's a template specialization for those macros generate template specializations for this like type descriptors, and they're actually cached, so they're not regenerated every single time. And there's built-in specializations provided for all primitive types, so it knows what like an int or uint 32 or whatever it like is. And so most importantly, as I've said, downstream code can make use of those upstream specializations. So this code, it's not open source, it's not on GitHub, but we would be happy to share it if there's any interest in that. A few more things. So one of the most common complaint is multi-threaded reading, writing, and you could say, okay, I could use multi-processing, MPI, and all of that. But for certain types of applications, the most performance ways to use multi-threading, especially if you have some weird shared state thing like in the middle that you can't really fork. And so the worst thing is if you have columnar, you need to access data in columnar way, and each record may end up being in a separate chunk. And if you have like 50 processes written same thing, and you end up actually copying things a lot. And we haven't really found a solution for that other than just transposing everything. So that would be nice to think about. One idea that a few of my colleagues suggested is whether it would be feasible to write a separate multi-threaded read-only, like bare-bones stripped-down version of the library, which would just have like H5D read and that's it, nothing else. But it would be like super fast. It would work with multiple threads. Again, I'm not maybe just bypassing most of the HDF5 internals, maybe skipping all the swimmer stuff, maybe complex hyperslabs, all of that. Just like bare bones, read it all, maybe contiguous slices. I think that may help a lot, like in some applications. And finally, writing login to different files in multiple threads. Again, it doesn't. I think it doesn't work because there's some like global variables and global states that gets messed up, like in the caches. But it sounds like it should work. So you're writing to different files completely. And I think then it would make HDF5 a lot a much better platform for like login in general, because it's quite typical to send things to multiple threads to write them. And so the last few things is the metadata lookup. We sometimes end up with partition data with let's say 50,000 data sets and not so much data, at which point those lookups over those like span trees and stuff, they actually start taking more time than reading the data itself. And again, we tried repacking metadata in like larger 1 megabyte blocks and stuff like that, but it doesn't really seem to help. So at this point, I'm not sure what's the idiomatic way of like handling this kind of files. And finally, most importantly, BLOSK support in H5Py. Now, if BLOSK, for some reason, if it stopped working tomorrow, we would probably consider switching to like tiled views or something like this. This is an extremely important part of HDF5 for us, which is not really part of HDF5. But so cheers to Francesc for building like CBLOSK and CBLOSK2, which kind of leads to the next talk. If you let me be opinionated, I think that the game is over. It has been over like 4 years ago. It's done. Like gzip, szip, it's not really feasible. Like for us, we've done tons of benchmarks which we can share, both regarding read speeds, write speeds, etc. Especially when you want to do shuffling, like bitwise or bytewise shuffling, BLOSK allows you to use SIMD, single instruction, multiple data kind of thing, which speeds things up like massively. And so H5Py is the most popular HDF5 interface, which is awesome, but there's no easy way to link both. So in fact, I've opened a ticket, which is the most commented and upvoted tickets on H5Py 4 years ago, and I think Elena replied, and John replied, and Andrew Klett replied, and Francesc replied, and Thomas Caswell replied, and nothing happened, right? And so what happened, if you just Google BLOSK H5Py, that's the first thing will pop up, and every few months people just come from Stack Overflow and from Google asking, okay, how to do this, and there's some hacks. There's like import py tables, and then 32001, 009, 05 or something like this, which I just copy and paste like every time. I think it would be nice to just ship it with H5Py. Which I've said initially. I'm not sure how it would work license-wise. Maybe it's Francesc could comment on that. Maybe it should be shipped with HDF5 itself, like gzip and szip, and which are mostly inferior, like with the modern, types of data that we deal with. Again, I'm not sure how it all works license-wise. And finally, the one topic that came up in that ticket was the new HDF5 plugin discovery system, which I think doesn't really work for conda-based or like package-based approach, because you can't force your downstream packages to source activate anything or like conda activate anything. So like environment variable approach just doesn't work. If you build a package that uses H5Py and then requires BLOSK to read anything or write anything, you cannot rely on environment variables at all. You cannot force your users to actually set some variables, or users of the users of your package. So it would be nice if there existed some an alternative approach to telling HDF5, hey, there's a plugin there. Maybe it would be file based. Maybe it would like look in the same folder where the library is installed, or something like that. But we haven't found a way. Like maybe it does work. Maybe it's not in the docs. Yeah, and this pretty much leads to the next talk by Francesc. Thank you.
All right, I think we have time for a couple of questions. Questions or comments? Elena.
I just want to comment, thank you for those questions, but we'll talk about some of them at roundtable. So
Okay. Cheers.
There are questions.
It's more of a comment again. For my day job, I have some examples of using account install HDF5 plugins that do get correctly found at runtime.
Okay.
But it involves getting your account back just right.
Okay.
Making sure things are put in the right place. So it's all just a stick.
Okay. Thanks.
I was just curious to know why you have 10,000 fields or more for the dataset, because I think the idea behind HDF5, but in general, the hierarchical object orientation stuff is that you are mapping the fields you are using into the programs, also into the data model. Instead, it seems that you are generating them if they are 10,000, because I can imagine that you wrote 10,000 fields now. So maybe you should use a data system.
Yeah, I think it was like 1,500 or something like this. You can actually overflow it with 1,000, if I remember correctly. It wasn't myself, it was one of my colleagues. They think it mostly comes from the fact that it's not the same data type. Obviously, you have a mix of all kinds of like floats and ints that you can't really reshape into a multi-dimensional data set.
Thank you for the presentation. The question raised are very interesting, but to go back on it, I would be interested in knowing the real value of storing in HDF5. If you store them in a fixed point, the real number, or in floating points, which matters a lot when it comes to compression rate.
We don't use floating point stuff at all, especially in production. It's all integers always. The exchanges never send you any floating point stuff ever. It's always fixed point.
Just a quick question.
Thank you.
I would be interested in your benchmarks regarding this encryption. So if you can share them, or you can share the code which you use to generate your benchmark.
Where should I screen? Oh, with the.
Sure. Yeah. Thanks.
Right now we have to give it to Francesca.
Yeah, but we have to see it today.